Welcome to the second lecture, ALE 311T Network Analysis. In the last lecture, we saw homogeneous ordinary differential equations and how to solve them using standard methods in mathematics. Today, we're going to see non-homogeneous equations. These are the ordinary differential equations which have a forcing function. Non-homogeneous ODEs. So the general form of non-homogeneous ODEs is going to be, as we have seen before, an x and t, where x and t is the nth derivative of x, plus an minus 1 x and minus 1 t, plus this is going to continue till you have a1 x dash t, which is the first derivative, and a0 x t is equal to ft. So the difference is that this ft is not identically 0, so you get a non-homogeneous equation. The solution for a non-homogeneous equation, if it is given by, if say the particular solution to this equation is given by xt is equal to xpt, then another solution would be xt is equal to xct plus xpt, where xct is the solution of star, that is this equation, with ft identically 0. In other words, this means that the solution, if this non-homogeneous equation has a particular solution given by xpt, then the general solution is going to be xct plus xpt, where xct is the solution of the homogeneous counterpart of this non-homogeneous equation. And you can very easily verify this by substituting the solution xct plus xpt into this equation. So when you do that, you'll see that the left hand side will be equal to 0 plus ft, and the right hand side is ft. So the general solution consists of two parts. It consists of the solution of the homogeneous counterpart of the non-homogeneous equation and the particular solution to the non-homogeneous equation, the sum of the two. By a theorem in mathematics which is called the uniqueness theorem, it is proven that xt is equal to xct plus xpt is also the unique solution to this non-homogeneous equation, because if the initial conditions at t is equal to 0 plus are satisfied. This is a theorem in mathematics. I'll repeat. xct and xpt as defined earlier. The sum of the two is the unique solution to this differential equation by the uniqueness theorem if this solution also satisfies the initial condition at t is equal to 0 plus. So what are the steps required to solve the differential equation, non-homogeneous equation? Number one, we find the particular solution xpt. Number two, we find the solution called xct, which is called the complementary function. This is the solution to the homogeneous counterpart of the differential equation which we are trying to solve. This is the particular, it is also called the particular integral. So you find the particular integral, you find the complementary function, you write down the solution as the sum of the two, and you make it unique by substituting the initial conditions. So these are the steps that are needed to be taken to solve a non-homogeneous differential equation. Many of these you have done before, but still, to clarify this and make it clear, we're repeating it. Now, there is a rule of thumb for determining xpt, the particular integral. We already know how to find xct, the complementary function. This is found by using the method for homogeneous differential equation. For xpt, the rule of thumb is that xpt takes the form of the forcing function ft plus all its derivatives. All its derivatives. So if the forcing function is, for example, say the forcing function is, for example, alpha e to the power beta t, the particular integral is going to take the form of the forcing function and its derivatives. So where alpha and beta are constants. So if you see this, it's very clear that all the derivatives of ft and ft itself can be written together as a e to the power beta t, because no matter how many times you differentiate, you will get a beta here, which is a constant. So the particular integral will take this form. What is left for us to evaluate is only the coefficient a. And suppose we also had the complementary function which was given in the form c e to the power pt, as we have seen before, for which we had to evaluate the coefficient c. So the total solution is going to be something like this, where this is the particular integral, this is the complementary function, this takes this form because of the form of the forcing function. Sorry. So this is a e to the power beta t plus. So this takes this form because of the form of the forcing function, and this is evaluated by finding the characteristic equation hp is equal to 0, the roots of the characteristic equation. So what is left after this, the third step, is to find a and c. So a has to be found and c has to be found. These are coefficients which are undetermined, and they need to be found through our knowledge of initial conditions. Right? So that's why this method is called the method of undetermined coefficients. So let us see what is the form that our forcing function that our particular integral takes for different kinds of forcing functions. Again, you'll have a table here similar to the table that we had in while we were solving homogeneous differential equations. So let me use this space also. So what is your forcing function? And what is the choice of your particular integral? So which is xpt. So if your forcing function is, for example, some k e to the power gamma t, your particular integral is going to be some other constant c or d or whatever you like, e to the power gamma t. This is the undetermined coefficient. If your forcing function is k t to the power n, where your n can be any integer 0, 1, 2, then your particular integral is going to be c1 t to the power n plus c2 t to the power n minus 1 plus this will continue till you get c0. If your forcing function is k cos omega t, particular integral is going to be k cos omega t, and if you differentiate this you'll get a sinusoidal term. So this is k1 cos omega t or c1 cos omega t. Let us write c1 cos omega t plus c2 cos sine c2 sine omega t. Similarly, if it is k sine omega t, we'll get the same thing here. If it is, for example, say k e to the power alpha t cos omega t, you should get c1 e to the power alpha t cos omega t plus c2 e to the power alpha t sine omega t, because this is the form of the derivative, general derivative that you will get. So basically this is what you're going to do. You're going to assume a form of the forcing function of the particular integral based on the forcing function that we have, and then we're going to determine the undetermined coefficient. This method works for almost pretty well in network analysis. It may not be very well suited uh, to every kind of function, but for the kinds of forcing functions that we have in network analysis, the method of undetermined coefficients works pretty well. So we're going to use this method to solve differential equations. Now let us take some examples and see whether we're able to do them well or not. So let us first see some equations that are homogeneous and which have certain initial conditions given. For example, let us say that we need to solve a differential equation which is given by x double dash t plus 8x dash t plus 16xt equal to 0, and The initial condition is given. Remember that we'll need two initial conditions for this because it's a second order differential equation, so you'll have two undetermined coefficients in this because it will have two roots, as the characteristic equation will be of second order. So two initial conditions are required, so they're given. X0 plus is plus 1 and X dash 0 plus is minus 1. 0 plus means just after 0. We have to differentiate between 0 plus and 0 minus because of certain restrictions that we have. You can in the beginning understand it like this. For example, we have a step function. Step function is something that begins at 0 and then remains 1 throughout. It's an idealized function, so it remains 0 up to 0. At 0 it has no defined value and it becomes 1 after 0. So how do you know the value of the function at t is equal to 0? You know that at 0 minus, just before 0 it is 0, and you know that at 0 plus it is 1. So you need to differentiate between uh, the value of the function at 0 minus and the value of the function at 0 plus. That's why you have initial conditions at 0 plus. This is a very rough way of saying it, but I think this should be sufficient for us to take 0 plus and 0 minus. 0 plus means just up to 0 and 0 minus means just before 0. So if we have this homogeneous differential equation and we have to solve it, we'll write down the characteristic equation. P square plus 8p plus 16 is equal to 0. And then we'll see that this means that p is minus 4 because you can write this as p plus 4 whole square is equal to 0. So you can write down the solution as c1 e to the power minus 4t plus c2 t e to the power minus 4t. And now to find c1 and c2, we need to put in the initial conditions that are given. So what are the initial conditions? Initial conditions are x0 plus is 0. 0 plus is substituted as 0. So c1 e to the power 0 is c1 plus c2 into 0 because t is 0. So c1 is 1, and similarly we'll have to differentiate this. X dash t is equal to minus 4 c1 e to the power minus 4t minus 4 c2 t e to the power minus 4t, which is the first differential, and then again differentiate plus c2 e to the power minus 4t. Put in t is equal to 0 plus in this. So on the left hand side you have x dash 0 plus, which is minus 1, and on the right hand side you have minus 4c1. This is going to be 0 because there's a t here, plus c2. c1 is already 1, so c2 will be minus 1 plus 4c1, that is minus 1 plus 4, that is 3. So c2 is 3. So the solution is let me use a different color. Xt is equal to c1 is 1, so e to the power minus 4t and c2 is 3 plus 3t e to the power minus 4t. So this is the solution for our problem. Now let us take the same problem, right? But let us now say that the question is not about solving a homogeneous differential equation, but it is about solving non-homogeneous differential equation. So there is some excitation, and let us suppose that the excitation is constant. So the excitation is, say for example, 10. It's constant. So the solution is going to be again xct plus xpt. We already know xct. We have found it because we have found the solution of the homogeneous part. So it was c1 e to the power minus 4t plus c2 t e to the power minus 4t. Suppose the initial conditions are the same, so x0 plus is equal to, what was it, x0 plus is 1 and x dash 0 plus is minus 1. So the initial conditions remain the same. Now we don't apply initial conditions on this because the initial conditions are not for xct, they are for the total solution, right? So the initial conditions are for the total solution, not for the solution of the complementary function. So they are applied when you get the total solution. So till now we have found that the complementary function is this. The particular integral takes the form of the complementary function of the forcing function plus its derivatives. So the forcing function is a constant. Ft is 10, which can be written as 10 exponential 0t. So your particular integral, if you look at the table, you can write it as, again, this 10 is not going to remain the same. It's going to be some a or b or c, a constant, but this e to the power 0t is going to remain the same. So the particular integral is going to be a constant. So the total solution can be written as the sum of the complementary function plus the particular integral. So which is c1 to the power minus 4t plus c2 t to the power minus 4t plus a. This is the solution. Now use the initial conditions. The initial conditions will give you at t is equal to 0 plus x 0 plus is going to be c1 plus a, because t is equal to 0 plus is substituted as t is equal to 0. So this is going to be c1 plus a is going to be 1, and then add differentiate this. So x dash t is going to be c1 is equal to minus 4t into minus 4 plus c2 is equal to minus 4t minus 4c2 t is equal to minus 4t. Again the same thing, but a is going to be differentiated as 0. So x dash t at t is equal to 0 plus, the left hand side you'll have minus 1, on the right hand side you have minus 4c1 plus c2. So these are the two equations that you get. So you see here that you have two equations, but the number of unknowns is 3. So you have two equations, but the number of unknowns is 3. So how do we solve this? We already know that xpt is a particular solution to this equation, to this problem. It's an independent solution with homogeneous differential equation, but it's not a general solution. So if xpt is an independent solution, irrespective of whether it has an xct added or not, it means that if we substitute this back into the original equation, we should get the left hand side and the right hand side equal. So that will give us a. So if we substitute xpt if you substitute xpt is equal to a is equal to xt, because it's a particular solution to this non-homogeneous equation, we get on the left hand side the double differential of a, which is 0, the single differential of a, which is 0. 16 times a is 10. 16 times a is 10. So this gives us a is 10 by 16, which is 5 by 8. So this gives us C1 is 1 minus 5 by 8, which is 3 by 8. And this gives us C2, which is minus 1 plus 4 times C1, which is minus 1 plus 4 times 3 by 8 is going to be minus 1 plus 3 by 2, which is minus 1 by 2. So we have the values of the 3. A is 5 by 8, C1 is 3 by 8, and C2 is minus 1 by 2. So the solution is obtained by putting these three values in the original equation. So the solution is going to be this final solution, which is unique because the initial conditions are satisfied, is 3 by 8 to the power minus 4t plus minus 1 by 2 t e to the power minus 4t plus 5 by 8. So this is the solution to the non-homogeneous differential equation. In the next part, we will see how to solve a couple of more equations which are non-homogeneous in nature, and then we'll move to the evaluation of initial conditions.